Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am starting module 8 and now from module 8 onwards I will be delivering the lectures on the topics of shells. So, I have covered the plates whatever is required, and there are many advanced topic also in the plate, and those who will be doing research in future they can take the course of advanced topics such as vibration of plates, then post buckling behavior of plates, composite plates, etc. And but the courses or the topics that I have delivered in the portion plates will be useful to follow the advanced topics. Okay. So, today introducing to you the shell structure, and the first lecture will be devoted to the characteristics of the shell, which can be taken as a stress skin. Now, outlines of this lecture is: first we will define the shell, then shell action I will discuss in relation to beam, arch and plate. Then I will discuss one interesting thing, that how the structural material can be efficiently utilized in various member in extensional or bending mode or combined mode. So, you will get a glimpse of the structure which are most efficient in utilization of the material, because the shell which you know this is a thin structure that I have told you during my introductory lecture introduction in the first beginning of the module. There I have mentioned that shell is a thin structure, and thin structure generally the material consumption is less. Okay. Then I will give you a differential equation of the stressed membrane, because this is a very classical equation in our mathematical physics or mechanics, and as a learners of this course plates and shell, we should not miss this equation, this membrane equation. So, I will discuss this and its solution method. Then I will take an example of square membrane to illustrate the solution of the differential equation. Okay. Now, you can see the term shell is generally related to a very hard cover, thin cover, and which possesses strength and rigidity. Okay. So, in nature there are so many examples of shell. Say for example, our human skull is also a shell. Then shell of an egg, this is hard cover and very thin. So, this is actually the shell is protecting the inner material. So, this is also behaving like a shell. Then some marine creature known as kukli is also having a hard outer cover which is thin and which is protecting the inner soft core. So, therefore, shell is understood as a hard thin cover, outer cover, which possesses strength and rigidity. So, from this characteristic we can see there are many engineering applications of the shell, especially this roof covering that we want for covering a large area. The shell is frequently used, and there are also application of shell in pressure vessels, pipe, then tank, or even the space vehicles, and many other examples are there where shell is used and this utilization of material in shell is very efficient because it is very thin and acts like a stressed skin. Okay. So, if I tell you the engineering definition of the shell, the term shell is understood as a thin curved surface acting like a stress skin. So, that is the engineering definition, and this definition has been adopted in Indian Standard Code IS 2210 1988. This code is actually the code for the design of reinforced concrete shell and folded plate. Okay. Now, in engineering application, shell can be constructed with various materials such as reinforced concrete or steel, but this code is specially devoted to the reinforced concrete shell. Now, shell are generally used as roof in our civil engineering construction practice for large area which must be column free, and also sometimes for aesthetic reason the architecture prefers shell in large areas. For example, the in stadium or assembly halls, marketplace, religious places, auditorium. In many other cases, the roof in the form of shell of various geometry gives a pleasing appearance. So, therefore, shell has various application in civil engineering construction, but it is not limited only in the civil engineering field. Shells are also found applications in pressure vessels, pipes, vehicles, aircrafts, liquid storage or grain storage structures, cooling tower, etc. So, there are various application, and people have seen that shell has very efficiently performing or very efficient in resisting the load, especially the self weight and other live load, and therefore, it is used for construction of various important structures. So, in nutshell, we can tell that shells are generally thin structural elements which acts like a stress skin. Now, let us see an example. It is a very well known example of shell construction, that is a Royan Central Market near Paris in the place La Defense. It is in the neighborhood of the Paris, 3 km distance from Paris. It was built in 1955 by renowned architects and engineers. Now, this shell roof you are seeing here covers a area whose diameter is 52.4 meter. So, it is covering an area of 52.4 meter and structure is round shell. Okay. This thin, you can see the thin structure, the thickness is very small, and it is supported on periphery by 13 points by pillars, okay, or by short columns. The central height of the shell is 10.5 meter. So, it is almost a 3-story building height, the central height, and thickness of the shell is only 80 millimeter in compared to its diameter 52.4. So, if we see the thickness diameter ratio, you can see it is thickness diameter ratio is very small, 1 by 655. So, this is the advantage of shell construction, where it is used as a obstruction free structure. That means, if in a marketplace or assembly halls or auditorium or even in the stadium, when we want that intermediate pillars should be avoided, then we go for shell construction, because in that case a thin structural element can be used to cover large span. Okay. So, this example is a very renowned example of shell construction and civil engineering practice, and it is the actually Royan Central Market near Paris. Okay. Now, you can see other application of the shell, say aircraft. aircraft fuselage, the main body of the aircraft, where passengers and cargo are housed. This is, you can see, it is a round shell. So, it is a closed shell and it acts like a stress skin, this aircraft fuselage. So, the construction of many important structure in space vehicle are also done with the help of thin elements like shell. So, therefore, shell has gained importance among the practicing engineers and designers, and among researchers also, because the shell analysis is complicated because of presence of curvature. So, that we will do here, full course will be devoted to the stresses which is produced in the shell under the action of the load, and therefore, we have to deal with the curved structure, but it is thin. Okay. So, this aircraft fuselage that you are seeing here, it is a monocoque structure and it is manufactured by Boeing company. So, you can see the vivid example of shell. Now, if we see the advantage and disadvantage of the shell, first, the high strength weight ratio is achieved in case of shell. Because of the reduction of thickness, the self weight becomes less, whereas the strength and rigidity is high, even the thickness is small. So, that is one important aspect of shell structures. Strength weight ratio is very high, therefore, it is preferably used in the aircraft structure where weight reduction is prime consideration. Okay. Then other advantage, if we see, the less material consumption is there in case of shell. Less material consumption, I mean that because of thickness, suppose for example, a concrete shell or reinforced concrete shell, which is covering the 52.4 meter span in diametrical direction, then you can see that thickness requirement is only 8 centimeter. Whereas, if I construct a single span beam of 52.4 meter, then reinforced concrete construction, simple reinforced concrete construction is prohibited, because the thickness requirement will be very large. So, in that case we can actually adopt the other type of structure, that is this suspended roof or this composite steel plate girder construction, that can be also used. But material consumption in case of shell is very less, and therefore, it is preferred, it becomes economic, and large column free area, that is one advantage that you have seen here in the marketplace, where no column is there inside and it is supported on the periphery only. So, the users, that is people, will not be obstructed by intermediate column. So, that is one important aspect of the shell construction, that is large column free area. Then aesthetic is important, because it attracts many people, and therefore, the aesthetic is achieved. Aesthetic sense is very high in case of shell construction by giving suitable form of construction, okay. Especially the curved construction. Okay. Now, disadvantage of shells are also there, because the curvature, that is sometimes very complicated. You may have a single curved type of shell, or you may have a doubly curved side type of shell. So, therefore, form work is very costly, because it depends on the nature of the curve. Sometimes we want a part of a circle of sometimes we want a parabola, sometimes a catenary. So, to give a proper shape of the curve, the form work should be accurate, and it is a costly, generally it is a costly things. Then more skilled laborer are required for construction of shell to maintain the curvature and geometry. And the another important thing is that analysis is complex. Although these several advantages there in construction, but analysis is complex compared to the flat structure. Okay. Now, shell action let us see in relation to the beam, arch and plate. Now, beam actually it is a very common structural element, it is a horizontal member, generally a horizontal member with a straight line idealization that we can do in structural analysis, and whenever beam is loaded in transverse direction, then it receives the load mainly by bending. The normal thrust and other actions are minimal in case of beam. Okay. Now, if we see the plate that we have covered up to the 7th module, we have found that plate is nothing but direct extension of the beam theory, and in 2 dimension the plate equations are described, and plate stress resultant etc., are dependent on the 2 variables, because it is a plane stress problem. Now, in which load carrying action is also produced by 2-way bending. Now, because of 2-way bending, the plate is also economical compared to beam, and this is seen in our analysis also earlier. Now, if we tell about the arch, now what is arch actually? Arch is a curved member with 1 dimensional idealization. That is, there are various forms of arch. There may be a fixed arch, fixed at the 2 ends, 2 supports. There may be 2 hinge arch that may hinged at the 2 supports. There may be 3 hinge arch that is hinged at the supports and another hinge at the intermediate point, and the arch is also requiring some geometry, because the shape of the arch may be your parabolic, or it may be a part of a circle or any other curve, and because of the curvature of the member in this direction in the plane, this internal thrust are generated, because when a arch is loaded vertically downwards, say live load and dead load whatever may be, the arch will try to spread, the member will try to spread, but this is prevented by generating a reaction component at the support. So, this reaction component that is generated at the support is nothing but horizontal thrust, and because of that this bending moment in the arch is reduced by some extent, depending on this rise of the arch, that is the height of the arch member with reference to the datum. So, that is the advantage of the arch construction, that it negotiates lower bending moment, and sometimes the shape of the arch can be chosen in such a way that it is subjected to only internal thrust. For example, if I give a 3 hinge parabolic arch or an example of 2 hinge parabolic arch, which is loaded by uniformly distributed load throughout the span, then we have seen that bending moment at any point of the arch is 0, and therefore, arch is subjected to only mainly the internal action of the thrust, that is the whatever thrust is produced due to support reaction, it will be transmitted at the other sections. So, in relation to this, shell can be treated as a curved surface, because arch is a line element, beam is a line element, but plate is a surface element. So, shell and plate, improved version of plate is shell. So, shell being a curved surface element carries transverse load by generating internal forces in the tangential plane, called as in plane force or membrane forces. Now, in the plate also the membrane force is generated when the plate is subjected to compression or extension in addition to transverse loading. That is also possible, but one difference between plate and shell is that the plate is a flat structure and shell is a curved surface. So, the plate also acts producing the moment of resistance in the two directions. Now, in the case of shell, because it is a thin structural element, the loads are mainly resisted by membrane action, that is in plane forces are generated and that is resisted. Bending moment is minimum in case of shell, and only it is seen that when the shell joins a support, near the support the bending moment is predominant or significant, but away from the support the bending moment action of the bending is very negligible, and in that case the load is resisted by in plane force or membrane force. So, that is the characteristics of the shell. Okay. Now, if we compare the efficiency of the structural material in different modes, that is one mode may be your extensional mode or another mode may be bending mode. Okay. Extensional mode means here the structure is this acted by a load which is along the axis. So, this is we call extensional mode, and if extension in this load is in the opposite direction, that is it is compressing the structure, then it is a compressional mode. Now, in that case you are seeing a bar which is acted on by a load W at the end and length is L, will produce a stress, say whatever stress is in the cross section, say it is say sigma. Now, at the yield point, for example, it is a steel member, at the yield point this stress is considered as sigma y, and that we consider, for example, without factor of safety, I am considering this as the limit for comparing the efficiency of the material. So, in that case we can see W equal to, W is the load that is resisted by the structure, is equal to sigma y into B d. What is sigma y? Sigma y is the yield stress of the material and B is the width of the section and D is the depth of the section. Okay. So, cross section I have taken, for example, for illustrating this case is a rectangular. So, ultimately this W is equal to sigma y B d or sigma y into A. So, this is pure extensional member. Now, next let us see the flexural member. In the flexural member I am illustrating two cases. One case is your simply supported beam subjected to a vertical load W at the center. So, in that case we can see that maximum bending moment is produced at the center. So, now if we want the bending moment M in terms of W, it can be written M is equal to W L by 4, where W is the load, L is the span of the beam and 4 is a factor. So, how it comes W L by 4? The reaction is W by 2 and W by 2, and if we take moment at the center, it will be W by 2 into L by 2, that is the bending moment at the center. So, W by 2 into L by 2 is W by 4. So, maximum bending moment is W by 4, and therefore, the maximum stress we can calculate M by Z. So, now W is nothing but 4 M by L. So, M is sigma y B d square by 6, B d square by 6 is the section modulus of the cross section. Cross section is a rectangular. So, moment of inertia is B d cube by 12, and if you divide it by d by 2, it becomes B d square by 6, which is known as section modulus. So, section modulus multiplied by the stress, maximum stress, will give you the bending moment M. So, W is expressed as 4 W y sigma y divided by L into B d square by 6. After simplification, it becomes 2 by 3 sigma y d by L into A. This example I have taken, the simple examples I have taken only to compare the efficiency of the structural materials. Okay. That is why the extensional mode is giving you the economic option for efficient utilization of the material. Okay. Now, if I see the flexural member, which is one end is free and other end is fixed, that is a cantilever type of construction, and here we can see the maximum bending moment occurs at the fixed end, that is the root of the cantilever. So, here maximum bending moment becomes W into L, and therefore, this W can be written as M by L, where M is the maximum bending moment. Again, denoting this section modulus as B d square by 6 and sigma y is the maximum stress, then we can write that W load carrying capacity of this cantilever beam is sigma y by L B d square by 6, where the load W is acting at the free end, that is the tip. So, after simplification or arranging this term, we can write W equal to 1 by 6 sigma y d by L into A. Okay. Now, let us take a curved member, that is a what we told you, the arch element, because beam element, from beam element we now extend this to plate element. So, arch element we now extend this to shell element, because various shell theories in a simplified way can be visited by the arch action. So, that we will see later. So, therefore, arch action, let us see what happens. Now, it is a semicircular arch and subjected to a concentrated load at the crown, and it is hinged at both ends. So, therefore, the vertical reaction at the support will be W by 2 and here also W by 2, and it is a semicircular arch. So, span is 2 into R, where R is the radius of the arch. Now, bending moment at the crown, that will be the maximum bending moment, and if we calculate the bending moment at the crown, then we get W by 2 into R, that is the distance, horizontal distance W by 2 into R minus horizontal reaction into this distance. Now, horizontal reaction for such type of arch is calculated, and I am just quoting the result from this textbook of structural analysis. This is W by pi, and this result can be obtained by any of the known methods, say Castigliano's theorem you can apply here to find out the horizontal reaction W by pi, because it is a single degree indeterminate structure. So, it can be very easily solved for unknown reaction here. H is the unknown reaction here, because of symmetry we immediately got the vertical reaction as W by 2. Okay. So, maximum bending moment is M equal to W by 2 into R minus W by pi, this is the horizontal reaction, into R. So, after simplification and putting R is equal to L by 2 here, we ultimately get this term M is equal to 0.09085 W L. Okay. Now, this is the bending moment of the semicircular arch, 2 hinged, subjected to a concentrated load at the crown. So, maximum stress that can be produced before yielding. Now, this arch is subjected to, at any cross section if you see, it is subjected to a thrust, normal thrust, as well as the bending moment. Now, if I go to the crown section, the thrust is W by pi, that is the horizontal thrust, because the normal at the crown section is also horizontal. So, therefore, the direct stress in the section, this at the crown, it will be W by pi into area. Area was B by D, because we have taken a rectangular cross section, plus the stress produced due to bending. Okay. Now, bending moment is this maximum bending moment. So, maximum bending moment we have substituted here 0.09085 W L divided by section modulus. Section modulus, because it is a rectangular section. So, section modulus is B d square and B d square by 6. So, 6 goes into numerator. Okay. After simplification and arranging this term, we now obtain W is equal to sigma y into A, then a factor that is 1 by 0.3183 plus 0.5451 L by D, where L is the span of the arch and D is the depth of the section. Okay. Now, generally span is large compared to this depth of the section. So, therefore, L by D ratio is generally large, because D is small compared to L. Now, let us take this D by L as 0.1. Then, if we compare the load carrying capacity of different members, say first example say W, we can see the load carrying capacity of the member is 0.67 into D by L we have taken 0.1, 0.67 into 0.1 and B by D, area is B by D. So, ultimately we have tabulated this value that for this flexural member simply supported beam, we have tabulated it as 0.067 sigma y into A, B D is A. Now, for bar in axial tension, that is our first element, we got directly that W is equal to sigma y into A. So, therefore, this W is equal to sigma y into A. Cantilever beam we got say 1 by 6 sigma y, D by L now we put as 0.1 and A is the area of the cross section. So, we get 1 by 6 into 0.1, that means 0.0167. So, 0.0167 sigma y A, and in case of arch, after substituting this D by L was 0.1. So, L by D is 10. So, if I substitute this and calculate this factor, then it becomes for arch W is 0.173 sigma y into A. Now, comparing this all these load values, we can see that material is efficiently utilized. That means, material is utilized to the maximum extent with the same cross section of the member and same length, when it is the material is in the extensional mode or it is under uniaxial tension. So, that conclusion we have obtained, that most efficient utilization of the material is in the member which is under the axial tension. Next, followed by the simply supported beam, which is 0.067 sigma y into A. Next, followed by arch, arch will be 0.173 sigma y into A. Then we get the load carrying capacity for simply supported beam is the third in the third position, that is 0.067 sigma y into A, and lowest is the hanging structure, that is the cantilever, we get 0.0167 sigma y into A. So, from this analysis, a simple analysis, we can see that the maximum load for the same cross section and same material and this same member length or dimension can be achieved in case of the member which is subjected to only in the extensional mode. Okay. So, if we compare this pictorially, then we can see the axial loaded member is the highest in efficient utilization of the material. Then we have the arch. In the present case, we have taken an example of semicircular arch. So, the capacity is 0.173 sigma y into A. Then the simply supported beam, the capacity is 0.067 sigma y into A. Then we have the lowest is the cantilever beam 0.0167 sigma y. So, this example actually is taken to show you that the extensional behavior of the structure gives additional advantage to produce the in plane forces, and which is mostly utilized in the structure with a thin element. So, this is possible with the help of shell structure. So, therefore, the behavior of shell is like a stress skin, and if a skin, this membrane, you can consider it as a membrane, and it is stressed or it is acted upon by tension in uniformly in all direction, for example, then this whatever load you apply on the membrane, this will be resisted by tension. So, analogous thing is the string or the cable in one dimensional element. Okay. Though therefore, I want to give you the analysis of stressed membrane, which is a very interesting thing, and equation is a very popular equation in mathematical physics, or you can tell it in the structural mechanics. So, we should not miss this equation to know further analysis of the shell. Okay. Now, let us see first the differential equation of a stress membrane. Okay. Say this is a stress membrane which has any geometry, and S is the surface. Now, here you can see I have taken O as the origin here, and direction of x axis is here along the positive direction of x axis, and along the positive direction of y axis two lines are drawn, and we assume that tension in the membrane is same in all directions. So, here tension is T, here also it is T in the direction along the y axis it is also T, and in the end it is uniform. Okay. So, slope of the deflected surface of the membrane in x direction is del z by del x and del z by del y. What is z? Z is the function of x y, is the deflected surface of the membrane. Okay. So, in the present formulation we take the tension in the stress membrane is uniform, but it is not necessary that tension must be uniform. If tension is taken non-uniform, then of course, the differential equation will be complicated and solution will also be complicated. But for simplicity, let us discuss the case with a uniform tension in the membrane. Okay. So, here is the membrane that you are seeing, and suppose a deflected line is shown here, and at this point this length is dx parallel to x axis. So, I have taken a section or a line along the x axis. So, this is the surface or the line that you are seeing, it is a curved line actually, and this is the elemental length in the projected plane is dx, and z is the deflection at one end. At the other end the slope will be different. So, therefore, this the deflected value or deflected position of the point at this point will be z plus del z by del x into dx. Okay. This is the differential increment of the deflection. So, these are two deflection at the 2 points of the small element dx. Okay. Now, if I resolve the tension in the vertical directions, because we have taken the sides here say A B, along the sides A B total tension is T into dy. We are taking the tension is uniformly distributed, and it is expressed as a tension per unit length. Okay. So, here if I see the tension on the side A B, then it is T into dy is the total tension, and if our positive direction of the z axis is vertically downward, then its this component along the vertical direction or its projection on the z axis is vertical, projection on the z axis, because z axis here we have taken positive downward. So, therefore, negative sign appears here. So, its component will be minus T into dy into dz by dx. dz by dx is the angle. So, actually this T into sin theta, but since theta is small, the slope is small, we can take sin theta or sine of slope equal to slope only. So, minus T into dy dz by dx is the projection of the tension T dy on the side A B. here we got it. Now, on the other end, that is at a distance d x, the tensile, the side is C D, okay, side is C D, and there also the tension is uniform, okay, tension is uniform, but you are seeing here that the direction of the tension is reversed. Okay. Now, if I again project it, the tensile force T into dy on the vertical axis z, then this angle is your slope. So, then we get this T into dy del by del x into z plus del z by del x into dx. So, this is the projection of this T dy on the other end of this element of the side, this is A B and this is on the side C D. Okay. Similarly, projection of the tensile force on the sides A D and B C. What are the sides A D and B C? A D is the side which is along the x axis. So, T is total tension along the A D is T into dx. Similarly, total tension on the side B C is T into dx. Okay. So, what I get here, the projection of the tensile force on the sides A D and B C will be minus T dx dz by dy, and it will be T dx del by del y into z plus del z by del y into dy. Okay. So, that we have got the projection of these forces, that is the vertical component of the tension we got. And let us see what will be the externally applied forces on the membrane. We consider the air pressure on the membrane, which is uniformly distributed and its magnitude is q per unit area. So, on the small element dx dy, the total air pressure will be q into dx into dy. Okay. So, if we get the total air pressure and this is the component of the tension in the vertical direction, then we can form an equilibrium equation in the z direction. Okay. So, consider the summation of forces in the z direction to be 0. This is one component of the tension on the element A B. This is another component of the tension on the other end of the element A B. Like that, we have got the component of the tension on the element which is parallel to the x axis, that is your the element that the element A D and element B C. So, that will be here for element A B and element B C. So, that component we have written, and plus the external force, that is q into dx dy, and summation should be 0 for equilibrium condition, because the vertical force will be resisted by the component of the tension. And you can see after the simplification, that is if I do the term by term multiplication, then we get this into T dy dz by dx, and then we get here T del square z by del x square dx dy. Dx is already there and this double derivative will come here, d square z del square z by del x square. Then here I got minus T dx del z by del y, then plus we get this T dx del by del y del z by del y. So, that we got here, and for other term we get T into del square z del y square dx dy and external force q dx dy equal to 0. You can see some terms are cancelled. So, this term is cancelled, again this term is cancelled. So, then divide both sides by dx dy, you can see dx dy are common in all the terms here, whatever terms are left, and then dividing we get the final equation del square z by del x square plus del square z by del y square equal to minus q by t. So, this is a very common equation in mathematical physics, and it is physical meaning of this equation is that of the stressed membrane. So, when a membrane is under tension, and it is subjected to a air pressure Q, then the phenomenon is represented by the differential equation del square Z equal to minus Q by T, where Q is the air pressure and T is the uniform tension in the membrane, and del square here is the Laplacian operator, that is del square by del x square plus del square by del y square. Okay. So, then let us explain this method or differential equation that we have derived now to solve a rectangular membrane. Okay. Membrane can be of any shape, it can be of circular or any other shape, but let us see a solution for case of rectangular membrane, that is plane is rectangular and it is supported at the boundary. It is supported at the boundary. Okay. So, let us take the side of the membrane, it is 2a and other direction also 2a. So, this is a square membrane 2a by 2a supported at the boundary, taking central point at the origin. If I take center point at the origin of the coordinate axis, the deflected surface can be represented by a series. Okay. We take the help of series solution, okay, where B n is a coefficient and we take this function of x as cos n pi x by 2a and a function of y, that is y n. Now, this function cos n pi x by 2a is seen to satisfy the boundary condition at x is equal to, you see the x is equal to a, because it is a square membrane. If I take x is equal to a or x is equal to minus a, that is at the boundary, point is on the boundary at x is equal to a, then we can see that this equation is satisfied for all odd values of n. So, 1, 3, 5 etcetera up to infinity. So, therefore, if this is the solution of the equation and B n is a constant. So, this solution can be written as a series form, that is, if I expand the sum, that I can tell that B 1 cos pi x by 2a y 1 plus B 2 cos 2 pi x by 2a into y 2 plus B 3 cos 3 pi x by 2a into y 3, like that. So, the summation goes up to infinity, because infinite number of terms are there, but for practical computation we have to truncate the terms to a finite number. Now, substituting this in the differential equation, del square z equal to minus q by t. Del square z minus q by t was the differential equation of the membrane. So, if I substitute this in the differential equation, then we get that, you see that B n is a constant, and after substituting this we get the double derivative of y n d square y n d y square, and this when the cos n pi x by 2a is differentiated 2 times with respect to x, because this equation contains the second derivative of z with respect to x as well as second derivative of z with respect to y. So, when we differentiate this quantity with respect to y x 2 times, then this n pi 2a will come outside and the sign will be negative. Then here it will be n square pi square 4 a square and y n will be there, and cos n pi x by 2a will be common to all the terms. This is equal to minus q by t. Okay. Now, after that you can express this q by t in terms of Fourier series, or you can get it from the first principle, that is applying the orthogonality conditions of the cosine function. So, let us do it from first principle, that means I multiply both sides of this equation by cos m pi x by 2a. Okay. N is a integer. So, I again multiply both sides of this equation by cos m pi x by 2a. Okay. So, then multiplying this equation with cos m pi x by 2a, both sides I multiplied it, and then use the orthogonal property of the cosine function. So, after utilizing the orthogonal property of the cosine function, we get this this will be your this a, only a, and other right hand side will be in the integral form. Okay. Then b n is there, b n will be as a constant, and the in doing this operation we can see that when m is equal to n, then only the value will be existing. Whatever integral is there, integral will be here is a, because the limit is minus a to a. So, integral value will be this a only. So, now here you can see that when m is equal to not n, then all the integrals will be vanished. So, therefore, we get only one term. So, in general we get this b n into this d square y n dy square minus n square pi square by 4 a square into y n into a equal to this q by t cos m pi x by 2 a into dx. So, then taking this only the second bracket term d square y n by dy square minus n square pi square by 4 a square into y n equal to minus 1 by a b n integration of this 0 to a q by t cos m pi x by 2 a into dx. Okay. Now, this equation have to be solved for the value of y n. Okay. So, after integrating this equation, we now get the right hand side as minus q by t 4 by n pi b n into minus 1 n minus 1 by 2, okay, where n is a integer, but it will exist only for odd integers. Okay. So, we get this equation now, the right hand side now constant. Now, you can see this equation is a non-homogeneous equation. So, solution have to be obtained in two parts, one is homogeneous solution and other is particular integral. So, let us first obtain the homogeneous solution. So, in case of homogeneous solution, we put right hand side to be 0. Then let us assume that the solution is y n equal to e to the power beta y, where beta is the roots of the characteristic equation. Then after substituting this, if this is a homogeneous solution, then it must satisfy the equation d square y n dy square minus n square pi square by 4 a square into y n equal to 0. So, if I substitute this y n equal to e to the power beta y here, we will be getting this characteristic equation beta square minus n pi by 2 a whole square equal to 0. Now, this equation, characteristic equation, has two roots. One root is plus n pi by 2 a, another root is minus n pi by 2 a. Okay. So, solution now can be written as y n equal to c 1 e to the power minus n pi by 2 a into y plus c 2 e to the power n pi by 2 a into y plus y p. Now, what is y p? Because this y p is a particular solution because of the presence of non-zero term in the right hand side of the differential equation. So, that will be evaluated later on. Now, let us keep it as y p. Okay. Now, utilizing the following relation that we know from trigonometry, that e to the power a x plus e to the power minus a x divided by 2 will be cos hyperbolic a x, and e to the power a x minus e to the power minus a x divided by 2 will be sin hyperbolic a x. So, these two relations can be used here, and then it is simplified in this form. Say constants are renamed actually. So, a sin hyperbolic n pi 2 a into y plus b cos hyperbolic n pi 2 a into y plus y p. Y p is the particular integral. that we have not evaluated till now. Okay. Now, here particular integral will be constant, because if we observe this equation, we can see the right hand side is a constant quantity, because q is a constant term, T is a constant term, because this tension in the membrane is assumed to be constant, n is integer. So, it is a constant term, and B n is also a coefficient which is constant. So, therefore, this the particular integral can be treated as a constant. So, if I take the particular integral as y p, then substituting this in the differential equation, we get, because the differentiation of this constant term will be 0. So, this term will not be considered in the particular solution when you substitute y p here, because of the differentiation, and y p is constant. So, it will be 0, only this term will be coming here. So, n pi square by 4 a square into y p equal to minus q by t 4 n pi b n minus 1 n minus 1 by 2. Okay. Now, here, so y p can be found out now as this minus 16 q a square divided by n cube pi cube b n into t, and this index is there, because when n is put as a odd number, this function only exists. For even number of n, this solution does not exist, that we have illustrated earlier also, because when we integrated this function, and the result of this integration is this, and it is valid only for odd integers. Okay. So, particular integral is obtained, and this solution is now written, the homogeneous solution plus the particular integral. So, if this solution is written here, then the general solution now expressed as sin a sin hyperbolic n pi by 2 a into y plus b cos hyperbolic n pi by 2 a into y plus y p. So, you can see in this general solution of y n, we have the sin hyperbolic term, that is sin hyperbolic n pi 2 a n pi by 2 a into y, that is one term, plus cos hyperbolic term is also coming here, because of the two exponential terms in the solution, e to the power plus n pi by 2 a into y plus n pi by 2 a into y, and also minus n pi by 2 a into y, and utilizing these properties, we now get this hyperbolic function in the solution. So, solution is written in terms of hyperbolic function for convenience. Okay. Now, you can see here the membrane that we have taken, for example, here it is a symmetrical problem, that is the air pressure or whatever pressure is applied on the membrane is uniform, and the origin is taken in such a way that it is symmetrical about x and y axis. So, therefore, because of symmetrical nature of the problem, the deflected surface also is symmetrical. So, therefore, there should not be any odd functions in the deflected surface. So, if you see this function, the odd function is sin hyperbolic n pi by 2 a into y. So, this we can omit now in the deflection equation. Okay. So, deflection equation is now written as y n equal to b cos hyperbolic n pi by 2 a into y plus 16 q a square divided by n cube pi cube into b n into t into minus 1 to the power n minus 1 by 2. So, that is the deflection in the direction of y, that is the function y n. And now, we have to evaluate the constant b, because constant b is till now not evaluated, and it is evaluated applying the boundary condition. Okay. Since the membrane is supported along the edges, so and it is a square membrane. So, at y is equal to a, the deflection is 0. So, therefore, by substituting this, we ultimately get B equal to 16 q s square divided by n cube pi to the power cube B n into t into minus 1 n minus 1 by 2 divided by cos hyperbolic n pi b by 2 a. So, y n is now completely known, and it is after rearrangement it is shown like that. Y a capital Y n is 16 q s square divided by n cube pi cube b n. B n is the coefficient and into t is the tension into this minus 1 n minus 1 by 2 bracket 1 minus cos hyperbolic n pi y by 2 a divided by cos hyperbolic n pi b by 2 a. Actually, here this it is a square membrane. So, we can take this term as this. Okay. The deflected surface now z equal to x y is this. Okay. So, that we get here the deflected surface, and z is ultimately found as this b n into cos n pi x by 2 a into y n. So, therefore, b n will get cancelled from this quantity, and ultimately you will be left with this term. So, this is the membrane deflection, and this example I have taken to illustrate the state of stress in a membrane which behaves like a stress skin. So, shell is also a stress skin. So, we must know the membrane behavior, then we will go to the analysis of shell. Let us see what we have done in today's class. In this lecture, shell is introduced as stress skin. Application of shell structure in various engineering fields were mentioned. Advantage and disadvantage of shell construction was discussed. Thereafter, a very well known equation of stressed membrane was derived, and the solution of a rectangular membrane was discussed. Thank you very much.